Hi, good morning, guys. Welcome to Chen's backyard classroom today. Just want to go over certain things that you guys asked me to the Zoom meeting earlier today regarding the sample quiz for calculus 3.8, 3.9. Okay, so here's some of the problem. Okay, so now let's take a look at that. So 3.8, 3.9. So someone asked me about number 2, 3, and 4 regarding the sample quiz, and also number 7 and 10. So we'll take a look at that. So number 3 is a little bit different. It's a little bit difficult. This one is asking about the rate of change for the distance in between those two trains. So one train travels west at 160 miles to Cucumber City. Okay, so this one is going to west. Okay, so this one is number 3. So here's Cucumber City. Okay, so 2 west. And the other one, okay, well, let's just put in the rate of change. So let's say this one is dx over dt. So that equals 160 miles per hour. Okay, let's just check one thing here real quick. So make sure that you guys can see this one clearly. Let's look at that right here first. Okay, that's perfect. Okay, so 160 miles per hour, so going to Cucumber City. Okay, so the other train, so let's see. So while the second train travels south at 150 miles per hour away from Cucumber City. Away. And this one, so let's say dy over dt. So it's 150 miles per hour. And then at time t equals 0, the first train is 60 miles east. So 60 miles east. Okay, so let's say this one is 60 miles east. And then the second train is 20 miles south. So 20 miles south already. Miles east, so let's put this right here. So the other one is 20 miles south. Now this one is just getting longer and longer. So this one, for the first train, is getting closer and closer to the Cucumber City. So eventually, so we want to find out the distance, the rate of change of the distance of those two trains. Again, so this one is T1, and then this one is going to be T2. And then the time is going to be after 10 minutes later. So first thing that you want to do, you want to convert that to time from minute to hour. So minute to hour, so 10 divided by 60. So we got 1 over 6 hour. Eventually, you want to find out the rate at which the distance between the train is changing at time t equals 10 minutes. So now, let's go with that. So first thing that you need to do, so you need to find out the distance of the first train. Okay? So the distance of the first train, as you notice, this one is a right triangle. So we do know that we do have x squared plus y squared equals L squared. Okay, so let's start it off with this one. Okay, so the initial distance here is 60 miles. So that means the first train is getting closer to Cucumber City. And then while the second train is getting further down south. Okay, so we're going to find out the distance here as well. So let's start with the derivative of this. So we do have 2x times dx over dt. plus 2y times dy over dt. So that equals 2L times dl over dt. Now for those who might be wondering how to get x, the distance here. So the way to find the distance, so we do know that the initial time is t equals 0, and then after 1/6 hour later, okay, so let's see that which first train traveled, the distance. So 160 times 1/6, so we do have 160 over 6. So reduce, divided by 2, top and the bottom, so we do have 80 over 3. So it's 80 mile, well 80 over 3 mile. So that's for the first train. And then for the second train, so the distance that it travels, so what we got is 150 miles per hour, that's the velocity. And then going down south, so after 1/6 hour later, so 150 over 6. Reduce, top and the bottom, so we do have 75 over 3 mile. Now, but keep that in mind for the second train, so this one is getting further. So the initial distance is 20 miles, so 20 plus 75 over 3. And then for the first train, this one is getting a little bit closer. So what we got is 60 minus 80 over 3. Okay, so one is for x and one is for y. So let's find out what x first. So 60 minus 80 over 3. So multiply by 3, top and the bottom, so it's 180 over 3 minus 80 over 3. So we do have 100 over 3. That's the distance of x. And then for the distance of y, so we do have 60 over 3 plus 75 over 3. So then that one would be 135 over 3. Okay? So once you get those two distances, so you want to find out what L is. So again, this one you can finish that by yourself. So another one that we can find out what L is, so x squared plus y squared equals L squared again. But instead of taking the derivative, we're just plugging in the distance, so it's 100 over 3, quantity squared. And then plus y squared, so it's 135 over 3, quantity squared, equals L squared. So once you solve for L, you plug in a number right here. And then eventually you want to solve for dl over dt. And so that's the first problem, the one that you guys asked me about. So now let's see what else that we have for the rest of this. So number 3, let me go look at that. The notes that I wrote down here. Number 3, number 4, number 7, number 10. Okay. So the next one we have is number 4. Okay, so for number, so that one is quite similar. This one is also related rate. It's not similar. It's also another geometric problem with related rate. Okay, so we'll just resolve this first. So water pours into a conical tank of height 7 feet and radius 2 feet at the rate of 1.8 cubic feet per minute. And how fast is the water level rising when it's 1 foot high? Okay, so this one got to be a little bit careful with the rate of change with the height of the water. So back to the notes, so we're talking about the main equation and the auxiliary equation we need to set up for this. Okay, so we'll find out some things that's happening here. Okay, so first thing that I would like to do, I would like to draw the diagram. So we do know that's a conical tank. Okay, like this. So for the water. So we do know the height of the tank, it's 7 feet. Okay, so the height here. So that's 7 feet. And the radius is 2 feet. Now, gotta be careful with the variable that you set up here. So we'll talk about that in a minute. The rate of change of the water. So dV over dt, it's 1.8 cubic feet per minute. Okay, so now let's find out what else that we have. And the height of the water level rising. So this one is about 1 foot high. Okay, so now here's the diagram we have so far. So one thing that we noticed, the volume of the cylinder, well not cylinder, the conical tank, it's 1/3 pi r squared times the height. Okay, so we'll discuss about the variable and find out which one is the actual variable. Now one thing that we noticed, the radius is always remains constant for this type of problem here for the top. But the thing is that according to the water level rising, so radius is also would be considered the variable. And also the height, because that's keep changing. The radius here is getting smaller because that's another cylinder. So back to what we did in geometry. So let's say we do have this similar right triangle. So let me just zoom out the picture here. So here's the water level. So the original radius for the tank is 2 feet. But now getting down here is getting smaller. So the height, the original height, so this one is what, 7 feet? And then the height of the water level here, we don't know what that is, so let's say that's h. Okay? So this one will be considered the main equation. The main equation. But now, we need to set up the auxiliary equation for this. So the equation, that means we can solve for one variable in terms of the other. So one thing that we notice, so 2 over r, it's the same as 7 over h. By using the proportionality, the ratio. So the bigger radius over the small radius is the same as the ratio of the longer height over the lower height. Okay, so cross multiply, so we do have 2h equals 7r. And now one thing that we notice, the height, that would be considered a variable. And that's what we need to find out for dh over dt eventually. Okay, so we just take the derivative of this. So we do have, well, before you take the derivative, actually you want to plug in that, well, you need to plug in that r in terms of h. So let's just solve for r here. So once you solve for r, so that means r equals 2h over 7. Okay, so we have v equals 1/3 pi, coefficient constant. So radius, so 2h over 7, quantity squared times the height. So we do have 1/3 pi. So 2h over 7 quantity squared, we do have 4h quantity squared over 49 times h. So simplify this a little bit more. So 1/3 pi times 1 over, well, this one here, we can simplify this one all the way down. So let's see. So we do have 4 over 3 times 49. So 3 times 9, 27. 3 times 4, 12. Plus 2, 147 pi. And then h to the power of 3. Again, we're not taking the derivative here yet. We're just doing the substitution. So h to the power of 3, which is what? Just part of the equation here. And now from here, we want to take the derivative. So dv over dt. And that will be considered 4 over 147 times pi times 3h squared times dh over dt. So now you just left with dh over dt. And the height for this one, so for the water level, it's 1 foot pi. So you just plug in a number, and then you solve for dh over dt. And then dv over dt, that's just 1.8. So it's 1.8 equals 4 over 147 times 3 pi. We can put in 12 here, because 4 times 3, that's 12. And then the height, which is what, 1 foot high. Okay, so plug in that height, and then from here, just simply use calculator to solve the dh over dt. So again, this one is the simple quiz form, not the related rate problem. Okay, so now let's see what else that we have. So someone asked me about 3, 4, 7, and 10. Okay, we'll look at that. So 7 and 10. like it's going to be another related rate problem or exponential growth or decay. Look at this. Number 7 and number 10. So each one of those related rate problems takes a lot of work. So make sure that you guys leave some space. You don't want to squeeze all the work together, because by the time that I check the work, make sure that everything can be shown clearly, logically, reasonable. Okay, so if anything that doesn't make sense, so that's only considered no credit, or maybe only partial credit. Okay, so now let's see what else that we have for the rest of this. So the next one will be number 7. Okay, so for number 7, bacteria. Okay, good. So bacteria culture initially contains 300 member. Okay, so this one is not a geometric problem, so this one I can only write down the given information. So for y0, so that's 300. And it grows at the rate proportion to its size. So what this one is saying that dy over dt, so that equals k times y. Okay, so the sentence that's given here is saying that, so the bacteria, and it grows at the rate proportion to its size. Proportion, so that means there's a direct constant and then times the population. So 1 month later, it contains 1,200 members. So a month later, so that contains 1,200 members. So find the number of bacteria after 6 months. Okay, so now let's find out. So one thing that we notice, so for the population growth model, so y of t, it's always considered y of 0 times e to the power of kt. So one thing that we need to find out is the value of k. Okay, so we need to find out the population 6 months later. So in order to solve for k, so we can just start it with this. So initial population is 300, and then after that, so it's 1,200. Well, this one is kind of like what we've been dealing right now, coronavirus. So initially, we do have like a small amount of people getting infected, but after for a certain while, so it's going to be a lot of people getting infected. So it's an exponential growth model. So e to the power of kt. So k, which is the constant, we don't know what that is. So t, which is what? The time. So 1 month later, so that means 1. And then from here we can solve for k. So divided by 300 both sides, so we do have 40. So e to the power of k. And then take the natural log both sides. So natural log of 40 equals k. And then you want to rewrite the equation. So y of t equals y0, 300 times e to the power the natural log of 40 times the time. And for those who might be wondering, can I simplify this a little bit? Yes, you may. So 300, so that times, we do know that e to the power of natural log is 1. So this one is kind of like a power to the power, so we can just put it this way. That's a power, we multiply by the exponent. So this one got canceled, we just have 300 times 40 to the power of t. So that would be the actual model for the exponential growth for the bacteria. And then we need to find out the member after 6 months. So y of 6, so 300 times 40 to the power of 6. So basically this one you can do down the calculator. So this one is number 7 on the sample quiz. Okay, so now let's see what else that we have for the rest of this. And for those who might be wondering, why do I wear a lot of clothes here? It's a little bit chilly. It's a backyard, so that's why I wear a lot of clothes. So now the next one is number 10, half-life. Okay. So this one, let's see, the half-life of euquadium, it's 1.33 minutes. Okay. If we started with 500 milligrams, find the amount that will be left after 4 minutes. Okay. So again, so it sounds like the problem is considered exponential decay because that's half-life. That means, well, it's getting less and less exponentially. Okay, so now let's find out. So for the half-life, so we have 1/2, so times the initial population. So that equals the initial population times e to the power of kt. So we're still comparing the model, y of t equals y0 initial times e to the power of kt. Okay, so now let's find out. Okay, let me just write down the information here as well. So in order to get down to the half-life, it takes 1.33 minutes to get to the half-life. And the initial amount is 500 milligrams. And it's asking about the amount after 4 minutes later. So y of 4. Okay? So one thing that's missing here is the value of k. So how do you solve for the value of k? So the way to find out the value of k, we started off with the half-life model. So y0 basically can cancel them out. So we got 1/2 equals e to the power of k. Well, the time it takes to get down to the half-life, it's 1.33. So we got 0.5. So that equals e to the power of 1.33 times k. And now you want to solve for k. So once you solve for k, so you take the natural log both sides. So let natural log both sides here. And then isolate that variable. So natural log of e, that's 1. So natural log of 1 over 2. One thing that we notice, natural log of 1 is minus natural log of 2, using the properties of natural log. So 0 minus negative natural log of 2 equals 1.33k. So for k, so that equals negative natural log of 2 over 1.33. So now, once we find the value of k, so what you can do, you can just rewrite the equation with the model, the exponential decay model. So y of t equals y0, the initial amount for the sample, 500 milligram. So times e to the power of kt, so negative natural log of 2 over 1.33 times t. And that would be the actual model for the exponential decay. So now you want to find out the amount remains after 4 minutes later. So basically that one, just plug in the time, 4 minutes later. So 500 times e to the power of negative natural log of 2 over 1.33 times 4. And for those who might be wondering, can you simplify this a little bit more? Certainly you may, because this one is like a power to another power. So you can do that or just put it into the calculator. So just find out exactly what that is when you calculate it. Again, this one is number 10 for the exponential decay model. So now, another questions that you guys have is the homework. Okay, so let's look at that. Okay, so we can resolve this. So again, any questions that you have, so for the next Zoom meeting, just let me know, and then we'll do another video. So probably by next Monday or Tuesday before the tests. And also later today, I'm going to put out the other sample test video. So you see some of the sample questions. Okay, so now let's see what else I have for use of this. One sec. So another one that we have is 3.9, number 37b. Start it out there first. So for the book work, here's what we got. So section 3.9, number 37b. And then section 3.10, number 43. So someone just asked me about those two problems earlier today. Okay, so we'll take a look at that. So 3.9, again, that one is like a related rate. Okay, so 37. Good. That's actually, it's one of the problem I did for the lesson on the previous YouTube video for section 3.9. So a television camera is positioned 400 feet from the base of the rocket launching pad. So right here. So here's the launching pad down the bottom. So it's 4,000 feet away. So you do know that's a constant. And the angles of elevation of the camera has to change at the correct rate in order to keep the rocket inside. Okay? So the rate of change of the angle. So theta is right here, so that means theta is the variable, because this one keeps rotating. So d theta over dt, that's what we need to find out, looks like. And also the mechanism for focusing the camera has to take into account the increasing distance from the camera to rising rocket. And let's assume that the rocket rises vertically at a speed of 600 feet per second. So the rockets just keep rising. So the rate of change for that one, dh over dt. So this one is 600 feet per second. And the sun is shining at me right now, so it's getting hot. And it has risen 3,000 feet. Okay, so the height will be 3,000 feet. So how fast is the distance from the television camera to the rocket changing at that moment? So that one, we just need to find out dl over dt here. Okay. But someone asked me about part B, 37 part B. Okay, so let's look at that. If the television camera is always kept aimed at the rocket, how fast is the camera angle, elevation changing at the same moment? Okay? So part A, you just want to solve for dl over dt. So that one basically you can just use the Pythagorean theorem. So that one is like 4,000 quantity squared plus a squared. So that equals L squared. This thing here, that's L. So for that one, you can use the Pythagorean theorem to find out what L is. But for part B, that's the main concern for a lot of people. That's to find out the rate of change of the angle. Again, this one is one of the problems we talk about for the lesson. So basically, this one we're using tangent of theta. So tangent of theta, so then that will be considered h over 4,000. So take a derivative when you have two different variables. So one is the height, the other one is the angle, because this one's keep rotating. So it shows the rate of change. And the rocket, you know, the height just keep increasing because that's getting further away from the launching pad. So taking the derivative, so derivative of tangent of theta, then that'll be considered secant square of theta times d theta over dt. And then derivative of this would be 1 over 4,000 times dh over dt. Again, to solve for d theta over dt, basically just plug in a number. Okay? But you need to find out what secant square of theta is. So in order to solve for theta, well, basically you just need to use that the hypotenuse. Okay? So secant square of theta. So that one is just consider L, whatever L that you have over 4,000. Or you can just solve for theta by using that the ratio. So you can do it either way. So theta is the same as inverse of tangent of 3,000 over 4,000. And then you take the inverse of the ratio. Okay, so inverse of tangent of 3, 4. And then once you find out the angle, you just want to set up the ratio for this one here. So once you get that secant square of theta, plug in a number. So d theta over dt, it's going to be considered, okay, so dh over dt, so 600 feet per second, divided by 4,000. And then this one divided by secant square of theta, which means that's cosine square of theta times cosine square of theta. Because that would be the reciprocal. So cosine squared of theta, so that would be 4,000 over this. But again, once you solve for theta, you can just take the ratios on the calculator. So that's for part B. Okay. So this one is for number 37. 37, part B, for the book. Okay, so now let's see what else that we have. Number 43 on section 3.10, linear approximation. Okay, so let's look at that one. Okay, so it's very hot, so we do not check here. And also, just want to check that. To the back here. Okay, looks good so far. So the next one is going to be section 3.10, number 43. Okay, so section 3.10, number 3. Okay, so just give me 1 second. Okay, so that one is highlighted in red, so that means it's one of the AP sample questions. So we do know the graph. Suppose that only information we have about the function. So f of 1 equals 5. Okay, making sure that this one is the right one. 43. Yeah, it is. Okay, so here's what we know. So suppose that only information we have about the function f. So f of 1 equals 5. And the graph of its derivative is shown. Okay, so the derivative is given like this. Okay, so let me just draw the graph roughly. So it looks like it's exponential decay. And with a certain value, so here's 0, the initial position for that one. It's 0, 3. So 1, 2, 3. Okay, so this one shows that y equals f prime of x. And use that linear approximation to estimate f of 0.9 and f of 1.1. Okay? And now are you estimating part A too large or too small? Explain. Okay, so for part B, so you can just do the analysis afterward, but let's use the linear approximation. So one thing that we notice, linear approximation, so according to the formula, it's what? It's f prime of A times the quantity of x minus A, and then plus f of A. And for A, you want to choose the closest perfect number, such as like perfect integer or perfect square number. Okay, so let's find out. So f prime of, well, for x right here, so obviously is what? 0.9. Okay, so let's do the first one, 0.9. And then for A, I would like to use the closest perfect number, so that would be 1. Okay? So you plug in the number, so L of 0.9. So f prime of A. So f prime of 1. And then x minus A, so 0.9 minus 1, then that would be negative 0.1. And then plus f of A, again, negative 0.1 because I have 0.9 minus 1. And then f of A, that means it's f of 1. Okay, so f of 1, which is what, 5. We're going to plug in the number in a minute. So one thing at a time, so f prime of 1. So according to the graph here, so f prime of 1, let's find out what that is. So it shows like the grid right here. So f prime of 1 will be considered 2. Okay, so let's plot right here. So that's 2. Plug in a number times negative 0.1. And then f of 1, so f of 1 that's given already, so that's 5. So 2 times negative 0.1, then that'll be negative 0.2 plus 5, then that'll be considered 4.8. And then for f of 1.1, so basically you want to do the same thing. Okay, so f of 1, let's do right here. So L of 1.1. So f prime of 1 times 1.1 minus 1. Okay, so 1.1 minus 1 plus f of a plus f of 1. So f prime of 1, and that's 2 times 0.1, and then plus 5. So 0.2 plus 5, which is what? 5.2. And that's for f of 1. The one that we did here, this one is for f of 1. So what do you think about the approximation? Is that getting close? Is that too small or too large? So you want to do some analysis for this, for part B? Again, this one is number 43. Section 3.10. Again, you guys can always rewind the video or just fast forward anything that you have more problem to deal with. So please let me know. Okay, so thank you for watching this video today.